Okay, we're going to start then with chapter 2 lecture, which is Newton's laws of motion. Um, let's move on. Basically, uh, the first law of Newton has to do with inertia. Okay, um, basically it means that what is said here on the slide, uh, that objects they tend to stay in the way they are. They don't move without a cause. They don't change direction if they are moving without a cause. Um, so basically, in nature, things don't change unless there is a reason for them to change. In the particular case of the law of inertia, uh, we need a force. We will need a force for an object to change its condition in terms of motion. So if the object is resting, is not moving, it's going to stay resting and not moving for an eternity, unless a force acts upon that object. The force could be any kind of force, of course. But if there is no force, the object is going to stay exactly the same forever. And on the other hand, if the object is moving in, let's say, one direction, let's say we have a, a rocket moving in outer space and no fuel anymore, it's just moving out of the impulse, the velocity it had before it ran out of fuel. So it's moving on outer space. Let's suppose there is no gravity nearby, which is not true. There is always gravity, but let's assume there is no gravity. The object is going to continue moving in a straight line forever unless a force acts on that object. And the force could be a gravitational force, could be an object having an impact with this rocket, a rock, meteorite, or something like that. But if nothing like that happens, the object is going to stay moving exactly at the same speed and in exactly the same direction. That's the law of inertia. Now, there are a few examples of inertia in real life. I'm pretty sure you have experienced most of these. Um, for example, if you are uh, on an elevator and the elevator starts moving up, the instant the elevator starts moving up, uh, all the blood you have in your body is trying to stay wherever it was, because inertia means, in a way, that objects resist change somehow. So the blood will try to stay wherever it is, and as a consequence, it's moving more to your feet and less on your head, and then you can feel a little bit strange, dizzy. Uh, of course, elevators are made in a way that the speed is not, the acceleration is not that strong, so people won't have an impact. But if the acceleration was extremely strong, like in a rocket, you could literally fade and lose consciousness. Would you mind, somebody is typing? I don't mind if you do, but would you mind muting yourself? That would be better. Thank you. Um, just to go over a couple of these, uh, let's say riding a bicycle, you all probably experience that if you stop very suddenly with your bike, you may very well fly over the bike and maybe even losing teeth or something on the floor, because you stop, but the stop happens at the bike level, and your body will tend to fly over. So if you don't hold yourself really tight to the bike, you may just continue going the way you were going before you press the brakes, and that will end you having an accident. Another example which I like very much is, if you're drinking a cup of coffee, like say in the morning, you're going to work, it's very nice to have a warm cup of coffee, and then you go into the car, and the moment you accelerate your car, just out of impatience, you try to get a sip of coffee. Well, if you are accelerating your car or you are just starting to move your car at the same time you're drinking coffee, this is what happens. The coffee will try to stay wherever it was. And because it is inside a container, it's going to push back against the wall of the cup, and it's going to rise, and then it's going to overflow and maybe stain your shirt or your coat or whatever you have, or your sweater. So those are real life examples. There are a couple more here that you are very well come to read. And um, now that there is a second law of Newton, which is the law of acceleration. Now, we said before that an object in rest stays at rest, or if it is moving, will remain moving at the same velocity in the same direction unless a force acts upon that object. Well, now let's assume we're applying a force to an object. If we apply a force on an object, the object will accelerate. So every single time you see an object accelerating, it is because there is a force being applied to that object. That's the only way it could happen. It could also be changing direction. Like if you are driving and you are going around the corner, you are changing direction. There is a force acting on your car, changing that direction. That's also considered an acceleration, by the way. Um, so that's a condition. So now the acceleration of the object will increase as the force increases, and this is kind of common sense, correct? You are pushing a cart in the supermarket, and if you push harder, the car is going to accelerate, and if you push even harder, it's going to accelerate even more. The harder you push, the more it is going to accelerate. So the acceleration is going to be changing in the same direction as the force. So we call this directly proportional. So acceleration is directly proportional to the force. By the way, if you guys have questions, you can talk, or you can just speak. I don't mind. Okay. Just be sure that once you stop speaking, if there is noise around you, just mute yourself. So, however, going back to the law of acceleration, if you are pushing an object with a given force, let's say the same cart in the supermarket, you are applying certain amount of force, and then you dump inside the car more stuff, cat litter, you know, pet food, dog food, the big bag of, a bunch of different things. The car is going to have more mass. If you continue pushing with the same force that you were before, then the car is going to accelerate less. It's going to move also, but it's going to start accelerating at a slower rate. The speed is going to be changing at a slower rate because you didn't change the force, but you did change the mass. So if you increase the mass, you lower the acceleration. So if we wanted to express these two things, we could say, for example, if I increase the force, I decrease, I'm sorry, that's a mistake. I also increase the acceleration. On the other hand, if I decrease the force, I also decrease the acceleration. And that's common sense. A car with a bigger engine can develop more force against the pavement, and it will accelerate more, correct? Now, when it goes to mass, if I increase the mass, the acceleration decreases. Or if I decrease the mass, the acceleration increases. So you can notice that there is a difference uh, between these two sides. At the left, we notice that the force and the acceleration change in the same direction. At the right, you notice that the mass and the acceleration change in opposite directions. Oh, sorry about that. I went to the wrong slide for some reason. Okay. I had another PowerPoint open. Okay, so that's the law of acceleration. Now, if we express those relationships in a formula, this is the formula. Acceleration is equal to force divided by mass. So if I increase the force, I increase the acceleration. If I increase the mass, I decrease the acceleration. So mathematically, this formula reflects what we know by personal experience. So as force increases, acceleration increases. As mass increases, acceleration decreases. So we could solve a few problems with this formula. And this triangle that you see here is kind of a trick to remember the formula. If you are good in algebra, it's probably not going to be necessary. But if you feel you may have some difficulties, please feel comfortable to use. So let's see how this triangle works in these three different problems. Please understand that we have three variables. We have acceleration, force, and mass. And this is a relationship between those three values. So one problem is going to calculate a force, the first one. The second one is going to calculate an acceleration. And the third one is going to calculate a mass. Every time you're calculating one of the three, you are assuming that you know the other two, correct? So the first one, how much force is required to accelerate a 50 kilogram object 5 meters per second square? So 50 kilogram meters is the mass, 5 meters per second square is the acceleration. So I know the mass and the acceleration. So this is what you do. Since you need to calculate the force, let's delete the force from that triangle. So what we left is MA. It translates in mass times acceleration. You can see there is a multiplication sign now in red between M and A. So that's my formula. In the second problem, we need to calculate the acceleration. So you can see here, I'm going to first explain how to solve the problem, that we are going to solve it numerically. So I need to calculate the acceleration in the second one, so I erase the acceleration. Which means acceleration is force divided by mass. You see F is over m, so acceleration is force divided by mass. In the third problem, I need to calculate the mass. So as you can see, I have erased mass. So mass is force divided by acceleration. Now, let's solve the problems. The first problem, how much force is required? So for the first problem, we erase the force, correct? So we said, we got the conclusion that force equal mass times acceleration. So the force, which is what I need to calculate, is going to be the mass, which is 50 times 5. And it's going to be 250 newtons. Uh, in the metric system, if the mass is in kilograms and the acceleration is in meters per second square, the force is in newtons. So that will solve the first problem. In the second one, we need to calculate the acceleration. So I erase acceleration, correct? So acceleration is force divided by mass. Force is 100 and mass is 25. So my answer is 4 meters per second square, which is the unit of acceleration. You don't need to put the units all the time. You can just put them at the end, provided you are aware that you are using the right units in the process. So you don't want to use as a force a pound and then end having uh, saying that the answer is in meters per second square. That's not going to work. So you have to be sure that the mass is in kilograms. The third problem, the question is about the mass. So mass, I erase mass. So mass is force divided by acceleration. I know the force, which is 600 or 60, I'm sorry, and the acceleration, which is 3. So I get 2 kilograms. Okay? So that's how the problem works. 3 kinds of problems with this formula. That's all there is to it. You don't have a fourth or a fifth. For this formula, that's what you're going to have. Okay, so now there is something also interesting. Um, if you have an object in free fall, an object in free fall is an object that you drop, like you get a rock in your hands and you open your hands and let the rock fall. I have to add that free fall also means no air resistance, which is on Earth is never true 100%. But if you have a piece of rock and you drop it, you're standing on the ground and you drop it, that the air resistance is going to be very small. Of course, if instead of a rock you drop a paper, uh, then it's a different story. Because if you drop a paper, the air resistance is going to be very important. Okay, I have a few comments here. Um, is there any other way to write the problems to where it will not be in newtons? Um, listen, we need to stick to newtons in this class. Uh, kilograms and meters and seconds. Okay, we are going to be using only the metric system. If we start using different units, we are going to be in trouble. Yes, you could use other units of force uh, in real life, let's say. Okay, as a fact, you could use pound, which is also a unit of force, and there is also a kilogram force. But if we stick to the metric system, we are going to use newtons, at least in this class. But the concepts are the same, the formulas are the same. It's just that the units have to be consistent. Um, and I agree with Marisa. It should always be in newtons. Okay, so now we have this, and so if an object is in free fall, there is a force pulling the object down, correct? Which is gravity, is what we call weight. Any object that we release is going to fall because there is a force pulling it down. If I have a rock in my hands and I open my hands, the rock is not going to stay in the same place. It's going to move. It's going to accelerate as it falls down. If the object is accelerating, it means there is a force. And the force is the gravity pulling that object down. That force we call weight. Now, when we are on free fall, there is always a constant relationship between the force and the mass. For example, I have, let's say, a mass of 10 kilograms. That mass, let's say a rock of 10 kilograms, that rock is going to have a force of 98 newtons. The acceleration would be the force divided by the mass. If you divide 98 by 10, you get 9.8, which is the acceleration of the object as it is falling. But if the object, instead of 10 kilograms, has 1 kilograms, then the force is going to be 9.8. And when you make the division, you also get 9.8. So any object that you choose to do the same calculation, if we are on Earth, of course, you always get 9.8. And that applies to a very small object, and that applies to a large object. You get a huge pickup truck and a pebble. And both of them, again, neglecting a resistance, will have exactly the same acceleration. So if we don't have a resistance, like if we are in a vacuum, a hammer and a feather will both fall exactly the same way. It's kind of counterintuitive because we always think, well, the feather is going to fall slowly. Yes, because for the feather, the air resistance is way too important. But for the hammer, the air resistance is irrelevant. So if you remove air, like in vacuum, like you may have a tube and you extract all the air, and then you drop a hammer and a feather, they will both fall exactly at the same time, at the same speed, with the same acceleration. And as a fact, this was done in the moon. The first time they went to the moon, they dropped a hammer and a feather, and both of them obviously fell at the same time. And they hit the ground at the same time, but on the moon you don't have air, so there is no air resistance. So we have been talking about force, the force of attraction, but force is more than just a gravitational force. So what is a force in general terms? Well, it's basically a push or a pull. You can either push or pull in any direction, but it's push or pull. Now, every single time there is a force, there is an interaction between two objects. You cannot have a force uh, in one object by itself and there is not another object producing that force. I mean, force doesn't come in pills or in concentrates that you can say, okay, let me put this little force to this object, and then suddenly you have a force. The force has had to be applied by something, some other object. So it's always an interaction. Every single time there is a force, there is an interaction between different objects. So as it says here in the slide, always come in pairs. Of course, you can have force applies by direct contact. Like, I push with my hand a cart in a supermarket. So there is an interaction between me and the cart. Two objects, me and the cart. There is a force I am applying to the cart. But what happened is, yes, I am applying a force to the cart because the cart is accelerating, but I feel the force in my hand too. Because the cart is applying a force on me as well. Identical and in the opposite direction. And it is called the law of action and reaction. That's Newton's third law. So if an object A apply a force on an object B, this force in red, F, well, then the object in blue, B, is going to apply a force in the red object, identical, but in the opposite direction. And you know that if you punch a wall, you might open a hole in the wall if you are strong enough and you manage to hit where there is not a stud or anything like that. But at the same time, you can break your hand too because the wall is also hitting back. So these are examples of action and reaction. So um, you have a car accelerating. Oh, I was checking, Patricia. You said you lost sound. I'm glad you got it back. I'm sorry, I didn't got it earlier. Um, so we have a car, and the car is accelerating. It was at rest, and now it's accelerating, increasing the speed. By definition, if that car is increasing speed, there is a force applied to that car. If there is a force applied to that car, the car is applying a force to that something that is pushing the car. And that something happened to be the road, the pavement where the car is, pushes the car, and the car pushes the pavement back. It's pretty much how we walk. We push the pavement back, and as a result, the pavement pushes us forward. Let's say ground. It doesn't have to be pavement. So action and reaction. And you know that if you're walking on a very thin piece of paper, you can, as you push yourself, you can break the paper because you are applying a force on the paper. And maybe the paper is not strong enough. So this action and reaction. The same happened with a rocket. A rocket uh, is accelerating, moving to the right. So there is a force applied to the rocket because otherwise it would not accelerate, which means there is an object applying a force on the rocket. And that object is the gas. The rocket is releasing a gas. By release the gas, it needs to push the gas, like throw it away. Like just picture the gas as millions or trillions of little baseballs, and the rock is pitching those baseballs back. Well, that's fine. The baseballs are going away. The gas is going away. But the gas is pushing back and the rocket is accelerating. So if you could do this experiment, stand up on a skateboard and get a very heavy rock and throw it forward. What will happen to you? The skateboard is going to move backwards because yes, you're applying a force on the rock, but the rock is applying a force back on you, and that's going to move you as well. So you're going to end moving to the right, let's say, and the rock to the left. Opposite directions, action and reaction. And the same happened with gravity. Okay, as I'm holding a rock with my hands, there is a force pulling that rock down. Yes, but at the same time, that rock is pulling Earth up. Of course, being the mass of the Earth so gigantic compared with the mass of the rock, The rock experiences a significant acceleration, and for Earth is almost zero. But in reality, there is a real force. So, I'm lifting my pinky finger, and I know that the sun is attracting my pinky finger. Yes, but my pinky finger is also attracting the sun. Of course, the force is extremely small for the sun, means nothing. So it applies to every single situation when there is a force involved. There is always at least two forces, two objects, action and reaction. So here we have this illustration. So we have this little ball here, and the ball fell on Earth. I hope you could see it. Um, Let me play it again. The ball fell on Earth. So the ball has a mass and has an acceleration, and Earth has a mass and has an acceleration because the ball is pulling up the Earth. But because the mass of the ball is very small, the acceleration on Earth is very small. While because the mass of the Earth is very large, the acceleration on the ball is also very large. So one has a very large mass, a very small acceleration. The other one has a very small mass and a very large acceleration. But there is a force applied to both of them simultaneously, always. Acceleration is what balances this equation because the acceleration is going to increase or decrease depending on this relationship. Okay, this is basically the lecture of chapter 2. Um, I hope you guys got most of it, if not everything. I can now answer any questions, and please feel free to speak or type if you have questions, and I would be more than happy to try to help you with whatever questions you may have. On the other hand, if you guys don't have any questions, um, you don't need to stay. You can very well leave. I will be here on the next 25 minutes, available for any of you that decide to stay or come back within that time frame. But again, I would be more than glad to answer questions. Oh, you have a good day, Marisa, as well. Thank you. Okay, Angela, you have a question. Um, um, which section are you in? We have 5 sections. Angela, did you send the question to me directly, R. Vargas, or to somebody else? Because we are different instructors, and you may very well be in a different section. I typically answer every email I receive, but I don't know right now which is your section. Okay. Then I have not answered your question. The reason being because I don't think I have received your email. Um, Now I have available the section. I didn't have it. Yeah, you're in section 5. Um, you're in section 5. Okay. So I'll check your email and answer it immediately. Now I didn't get an email yet, but maybe just send it to Corinne for some reason. I think she's showing as the instructor of this class, which is not the case. So please resend back the email to me, which is R Vargas. R Vargas is R as Rose, V as Victor, ARGAS at fullcell.com. Please send me an email. Let me type it so you can have it, you can see it. And please send me an email and I will answer it immediately. For some reason, I couldn't. The FSO was not set to be. Didn't give me access to this course until just now. Basically, before this session started, I didn't have access. So you probably sent this email not long ago. Okay, you send an email with a letter from Student Success Service. Okay. Um, I will consider that. But please, if you send it to Corinne Rombach, I think should be to her. Please send it back to me. Okay. But well, I have your information, Angela Jones, right? And I know that you sent me that. Yeah, I don't have yet any message, and I didn't receive an email. So let me refresh. Maybe I will get it. Yeah, I'm restarting my Outlook just to be sure that I receive your email. It could be caught in filters. I receive a quarantine at the end of the day, and I think I got it. I got your email, Angela. I had not received it yet, but I have it now. And you had sent me another one a couple of days ago. Um, yes, I received, and I had received the other one. To be honest, the first one. Um, okay, yes. Um, okay, good. I have them here, so everything is okay. Um, I will keep your email and information. Okay, and please, if I can help you in any way, let me know. I will. Since now I have access, I will jump on this right away and catch up with everything I have to do. Okay. Thank you so much for letting me know and reminding me about this. You too, Angela. I'll see you soon then. Okay. Take care. Hi, Cardell. Uh, Cardell, can you hear me? Yes. You have a question? Let me know. Cardell, you can do it either way. It depends on the background you have. Like if you already took AP Physics or something before, uh, you may think that this is not a very difficult class for you. But if you need really to go over the material, obviously it would be more recommended that you go to sessions. Study, train yourself as much as you can before you do the assignments. Of course, you need to be mindful about the due date, but it's not mandatory. I didn't have any issues. Uh, I didn't have any issues, Cardell. Sometimes it happens, internet issues. Typically, what we do is we have the laptop, the same as you probably do, and we have an iPad, and we have a software that communicates the iPad with the laptop, and we use it to be able to write notes and draw things on whatever we are showing in the presentation. And sometimes there are issues with internet. I guess it depends on internet. We typically work from home when we do go to meetings, so we don't have the advantage of the very fast and reliable internet at Full Sail. I did earlier. Yes, the lecture was over. This is a short chapter. It's very important content, but it's a very short presentation. So I stayed a little bit more than half an hour in the lecture. So yes, I finished earlier. You have a nice day, Carl, too. Nice meeting you. Goodbye, Carl.